Good afternoon, everybody. Welcome to another exciting afternoon of Chem 1105 with your host, me, Dr. White. Hi, everybody. All right, let's go to Blackboard. And let me remind everybody, tomorrow I will be giving test number 3 online. It will cover chapter 6 and chapter 5, part 2. And it will have 20 problems, 9 pages, 5 multiple choice. Some of the questions are multiple part. And it covers 48 points, gases, 57 solutions. Remember, upload it by Friday. You have until Friday. You can't highlight Friday, 4 p.m. to upload it. It should take you about 40 minutes, 45 minutes. But if you need up to 3 hours, take 3 hours. I'm not going to sit there with a stopwatch. All right, now I will be posting scores by Sunday and also sending out your individual points for each answer by Sunday and in the private email. On Monday, I will go through test number 3 answers, but I'll cut it out of the video. And today, I already did a review on Tuesday, yesterday. All right, that's one thing I wanted to point out. Let me go to student view. If you go to assignment area, you'll see Chem 1105 extra credit for the summer 2023. And let's open one of those. And this is 10, yes, 10 big points. And how do you get 10 big points? You do this project. What is this project? It's to create a list of ionic and covalent molecules found in ingredients of products that can be purchased, i.e., by the way, that's Latin for that is, things you can use in your daily life. You must find 5 different molecules that contain ionic bonds, and it could also contain covalent, but excuse me, but it must contain an ionic bond, and 5 different molecules that contain only covalent bonds. You can use 3 molecules from any one product, which means if you got to do 10, you've got to look at at least 4 different products. You can have 10 different products if you want. Now, to get your points, you have to hand in, or I should say, upload a printed table with the product name, the molecule's name, and whether that molecule is ionic or covalent. Be sure to include your name on the table. You get 1 point for each correct answer. If you have 10 entries, 10 points. Now, one thing I should put out, if you put down 12 entries and 2 of them are wrong, I'm only going to give you 8 points. Why? Well, you shouldn't have put those 2 wrong ones down. And you cannot use gasoline, water, sodium bicarbonate, carbon dioxide, ethanol, also known as ethyl alcohol, sugar, sodium chloride, also known as table salt, oxygen gas, O2, nitrogen gas, N2, natural gas methane, which is CH4. Now, hi, Veronica. Oh, it's outside with Chem 1105.
I know, right? Hello, Dr. White.
Hello. By the way, you're not unique. What was it? Spring semester, I had a student who was on his way to Florida watching me in a van. Someone else was driving. Hi there.
See, he's my little scientist.
Well, I'm
He's
going to
gonna,
charge you extra. Oh,
yeah,
wait.
right, for an extra student, I bet.
It's a 2-for-1 sale. He comes. All right, let me get back to what I have to get going. All right, now we were talking about you can't use natural gas. This is for the extra credit project, which is 10 bonus points if you do it. An example of your chart, first column, product, second column, molecule, third column, bond type. And if you look at Coca-Cola, you'll see the first ingredient is water, and that's covalent. However, you can't use that because you can't use water. See, it says it right there. And another example would be Campbell's chicken noodle soup has sodium chloride, a lot of sodium chloride. Even the low sodium chloride salt still has a lot, and that's ionic. Now, this is important. Ingredients must appear on an ingredients list in a product. You can't say, oh, I have a banana. It has this chemical. And I can tell you some of the chemicals in banana, but I've never seen an ingredient list on a banana. You find one, show me. I'd be surprised. Doesn't exist. Now, this is totally optional. You don't have to do it. But if you do it and you get it right, you get 10 points, 5 and 5. That's 10. That's like getting 10 more points on any one of your tests. That's a good thing. This is not a group project. Don't or three of you use the same entries. I've had that happen over the years. I haven't told you this, but I have a photographic memory. When I'm grading, I say, wow, that looks just like so-and-so students. And I've caught people that way. That's called cheating. I will do what's in my syllabus for students who cheat. Please don't. Now, how can you tell if a molecule has ionic or covalent bond in it? Well, let me open up a periodic table and I'll teach you something real slow or quick. All right, now, if a molecule has an alkali metal, lithium, sodium, potassium, rubidium, you're not going to find any with those others, or an alkaline earth metal, magnesium or calcium, and if it also has an iron, like iron, lead, nickel, copper, palladium, silver, gold, platinum, and some others like tungsten, which I haven't talked about, titanium. But anyways, aluminum, if it has a metal in it, it's going to be ionic. It's going to have an ionic bond. Let me say that again. If you find a molecule in the name, it has the name of an alkali metal, alkaline earth metal, or just any metal like copper, nickel, iron, it's ionic. And let me show you an example. And let's see, are you seeing that? Let me check. Yes, you are. And here we have calcium citrate, and calcium is an alkaline earth metal. And actually, this is a product I use, Citracal, for a calcium supplement. But if you see any product with calcium citrate in there, you can put down the product name, then calcium citrate, and then it's ionic. Well, I just gave you one. Where is it? Hold on. Oh no. Here it is, hiding from me. I hope you're all familiar. This is a great product. I've been using it for many years. Carmex. You put it on your lips in the winter, keep it from getting chapped. And if you look, it's got an ingredients label here. And hold on while I do something very rare. Since my cataract surgery, I don't need glasses. If you go back and look at my old videos, I always wear glasses. Now I only need reading. If you see here, one of the compounds in there is phenol, PHENOL. Does that have a metal name in it? No. So phenol is covalent. Ooh, you can get more from here. You can get 2 more. This is a good product. Oops, upside down. You can tell I work on TV a lot. Ta-da. And all you have to do is, I will tell you, I don't need these anymore. Thank God. By the way, if you ever know anybody who needs a good eye surgeon, the one who did both my eyes, and they really were bad cataracts, Dr. Cabin, he's in Hoffman Estates. He's awesome. His staff is awesome. The surgical team he uses with him at where he's located is awesome. So, but anyways, that's the extra credit project. Now, as a special service to all my students, if you email me your project before you hand it in, I will check it and tell you which ones are wrong, which gives you a chance to change them. And then you can just send it to me again before you upload it. So that way, anybody who wants to get 10 points, it's not that hard. Now, let me give you some hints. Go into your bathroom and look at things there. Go into your refrigerator and kitchen. If you don't want to do that, walk down any aisle in a supermarket or big box store, either where the food is or where the personal care items like toothpaste, mouthwash, soap, and all those other good things. And within 5 minutes, you can get a list of at least 10 things you could use. Now, if you don't want to write it down, take your cell camera and take pictures and go home and look at the labels, or you can look online too. And remember, the deadline is August 1st, 11:59 p.m. After that, I will not accept any late projects. All right. Any questions on that? Going once, going twice. I'm opening up something for you. All right, as promised, I'll go through Chapter 5, Part 2, Solutions Problem Set. And hopefully you've done this for tomorrow's test. This will help you. All right, give an example of colloidal dispersion used in your daily life. Oh, I'm sorry, I have this. This was back when I still did, students still could read cursive. Oh, could I have one too? Anyways, milk, latex paint, and blood are all examples of colloidal dispersion. We'll give an example of a solution that you could use in your daily life. Pop, air, gasoline, tea. There are many more you could pick. Mouthwash, those are all solutions. Now, if a solution has 12 grams of KBr, potassium bromide, and 10 grams of water, what's the solvent and what's the solute of the solution? The solvent is always the component present in the greatest amount. I think you will know 12 grams are greater than 10, So KBr is a solvent. All other components are solutes, in this case, water. Normally think of water as a solvent, but it doesn't have to be. All right, next, number 6. What does 1.34 capital M HCl mean? And let me open up one other thing before I proceed, because I didn't. And if you look on your screen, you'll see what you'll see tomorrow. That's in the back of test number 3. And that's important information. And molarity, which I don't have on here, is capital M. Nope, that you got to remember is moles of solute per 1,000 milliliters. And now, when you see a number, capital M, and a formula, HCl, that means molarity, and this means 1.34 moles of HCl per 1,000 milliliters. Now, if we look at number 7, what does 4.56 times 10 to the third capital M NaCl bracket AQ close bracket mean? And what is the solvent of this solution? And if we look at that, we see capital M, number in front, formula afterward. That tells me anytime you see a capital M in chemistry, that's molarity. And that means 4.56 times 10 to the third moles of sodium chloride per 1,000 milliliters. What's the solvent of the solution? Well, bracket AQ close bracket is shorthand for aqueous, which means water, which means the solvent is water. Whenever you see after the formula of a molarity, bracket AQ close bracket, that means the solvent is water. All right, let's look at number 8. How many moles sodium chloride are 125 milliliters of a 3.45 capital M NaCl solution? Well, what are you being asked to find? Moles of sodium chloride. What are you given? Well, you have 125 milliliters of the solution, SML, and this number 3.45 capital M NaCl. Whenever you see that capital M and a number in front and a formula afterward, that's molarity. And you should know that's 3.45, in this case, moles of sodium chloride, NaCl, per 1,000 milliliters. So we have the 125 milliliters. We're trying to get the moles of sodium chloride. Whatever you're trying to get to, it's time to use your good buddy, your good friend, unit analysis, and we will. Whatever you're trying to get to goes on top of a ratio to convert the starting number to the units you want for your answer. And whatever you're trying to get rid of, I don't want milliliters in my final answer, you put underneath. And where do you get those numbers? From the molarity. 3.54, 3.45 moles of NaCl per 1,000 milliliters. Now, the first number, 125, is 3 significant figures. Uh-oh, he's in his rut again. And the 3.45 is 3 significant figures. Now, the 1,000, that's part of the definition, and that's an exact number. And when you're multiplying and dividing, which we are in this one, you get the same number of significant figures in your answer as the number that has the fewest significant figures that you multiply and divide by. Well, 3, 3, and notice this is 3 significant figures. I rounded off what was on the calculator. And 9, 10 are the same. Let's look at number 11. How many grams, and G is grams, of NaCl are needed to make 345 milliliters of a 6.789 capital M NaCl solution? So what are we being asked to find? How many grams of sodium chloride? What are we given? 345 milliliters of the solution and this number 6.789 capital M NaCl. Whenever you see a number capital M and then a formula, that stands for molarity. And molarity is moles of solute per 1,000 milliliters. Well, this one is 6.789 moles of sodium chloride. Excuse me, I got an itch here. No, I don't. Per 1,000 milliliters. Now, there's no way you can go from milliliters to grams in one step. There's no way you can go from milliliters to grams in one step. You can't. So what do? Well, in case you forgot, you look at important information and say, I need to use the molarity two-step problem. There's a two-step. Step one, we go from milliliters to moles. Step two, we go from moles to grams. So let's do that. Now in step one, milliliters to moles, we have these many milliliters. We're trying to get the moles of what? Well, sodium chloride. Whatever we're trying to get to goes on top of the ratio. You're using your good buddy, your good friend, unit analysis, and whatever we're trying to get rid of goes underneath. And where do I get these numbers? From the molarity over here. 6.789 moles of sodium chloride per 1,000 milliliters. Now, here I have three significant figures. Ooh, I got 1, 2, 3, 4 significant figures. Remember, the 1,000 is an exact number. When you multiply and divide, you get the same number of significant figures in your answer as the number that has the fewest significant. So you got 3, 4, which smallest number, times up. Hopefully I'll pick 3. And if you notice, I rounded it off. This is the calculator gave me a long number that you've seen me round off to 3 significant figures. Are we done? No. Here we're at moles of sodium chloride, but we need to get to grams of sodium chloride. So now it's time to do step 2. In case you forgot, step 2 is moles to grams. So in step 2, I want to do moles to grams. And here I have 2.34 moles of sodium chloride. I want to get the grams of sodium chloride. Whatever I'm trying to get to goes on top of the ratio, the units, grams of sodium chloride. Whatever I'm trying to get rid of, moles of sodium chloride, go underneath. Where do I get a relationship between moles of a compound and grams of a compound? Well, in case you forgot, you can look at important information, test number 3. Moles of a compound equals the molecular weight of that compound in grams. And the molecular weight of the compound is the sum of all atomic weights. And we'll need the atomic weight of sodium. The 3 significant figures is 23.0, and chlorine, which is 35.453, but the 3 significant figures, 35.5. Remember, on test number 3, just like on test 1 and 2, or 2 and 3, or that, Let me start that again. Remember on test 3, just like on test 2, it will say underneath your name, please use proper significant figures for all calculated answers, and please use 3 significant figures for all atomic weights. If you don't, I take off a point. Hope I don't have to do that. And now we know to get 1 mole, here we need the molecular weight of sodium chloride. And over here, the molecular weight is 1 sodium, 1 chlorine, and that adds up to 58.5. I do the math, 3 significant 3, the mole, 1 mole is an exact number, and my answer has 3 significant figures. By the way, I didn't write it, but I could have also written it 1.37 times 10 squared grams sodium chloride. Now, as I've mentioned numerous times, when you do multiple calculations in a problem, there's 2 ways of rounding off. One is round off at each step. And Dr. White, I'm a round off at each step person. Or you can round off at the end, which I don't do, but I'm not going to force you to do my way, because a lot of chemists I know do it the second way. Well, a lot more I know do it each step, like me. Therefore, I calculated both ways, rounding off at each step and rounding off at the end. If you notice, I have here both ways. That means if you round off at each step or at the very end, I like that hand signal, very end, whatever that means, but you get the same answer in this case. And same thing for number 12. And I'd highly recommend you look at problems 10, 11, and 12 for test number 3. And 13. Wow, I gave you a lot of practice problems. And with that, that's my coverage of Chapter 5, Part 2, Solutions, Practice Problems. And I'm trying to think, is there anything else I should cover? Nope, I think I covered it all. All right. And don't forget, I got to show my flashlight again. Don't forget, if you have a solution, light goes through it. If you have a colloidal dispersion, it scatters light, so it doesn't go through it. This is a multicolor. I don't know if you can see the color. It does bright red, and it does white, bright, and lower intensity. By the way, this gets so hot, if I hold a piece of paper here, you can set it on fire when it's on full blast. I love flashlights, in case you haven't noticed up here. All right, any questions about test 3? All right, let's get back to chapter 7, which will be on test 4 coming up next Friday. Sometime tomorrow, I'll post test 4 information. But let's get going. All right, yesterday I was talking about acids and bases. I talked about the Brønsted-Lowry theory, and I better get subtle again. Whoops, clicked on the wrong thing with my stylus. Sorry about that. Oh, guess what I did? I'll have to open it up again. I'll have to be careful where I put my stylus. All right. You should know that an acid, which normally nowadays the chemist says an acid, he's talking about a Brønsted-Lowry acid, is a proton donor, something that can donate a proton. And in chemistry, we show a proton by H plus. So you should know, hint, Brønsted-Lowry acid or an acid is a proton donor. And you should know, hint, know this, a Brønsted-Lowry base, if a chemist says a base, he's talking about a Brønsted-Lowry base, and that's a proton acceptor. Again, a proton is H plus. So an acid is a proton donor. If I'm an acid, here, take my proton. Take it, take it. If I'm a Brønsted-Lowry base, give me your protons. Give it to me. Give me your protons. And you should know this. Now, important thing happens in water. And a proton can react with water to form the hydromium ion. And it's actually a covalent bond. You have 3 hydrogens on the oxygen, and it has a plus charge. I'll never ask you what's the hydronium ion, but I will use that term this chapter. Now, it's Subtle Wednesday. In acids and bases, we have what's known conjugate acid base pairs. And first of all, I have to teach you something. Proton transfer between an acid and base doesn't occur 100%. Some are pretty close to that, but it's not 100%. And it has what's called an equilibrium. Now, in Chem 11, 1211, we go into a whole chapter on equilibrium. And here, we're not going to, but equilibrium means there's 2 reactions going on at the same time, from left to right and from right to left, and they go at the same rate. Now, it's shown by this double-headed arrow, the fancier one my software does. And if we look at this, and I'm going to rewrite this on my whiteboard so I can have some more room. All right, now, HA, let's call this an acid. And B, let's call it a base. Now, conjugates are molecules that differ by a proton. I'll never ask you what's a conjugate, but you'll need to know how to identify them. And if we look here, and I'm going to go Technicolor, notice HA on the left and A minus on the right differ by only H plus. Now, this is difficult for students to grasp their head around at times. I don't know why. Well, don't forget, I'm a PhD chemist, and this is quite fundamental, but students have a problem. Look for difference in this H, hydrogen. Forget about pluses and minuses. And HA is the acid. And everything on this side, I'm going to abbreviate, are conjugates. This is the letter C. Now, if we look at the base, I'll use a different color. What compound on the right differs from the base by 1 proton? And that's HB. So HA is the acid, B is the base. Now, if we go look at this reaction going this direction, remember acid proton donor, and it gave it to the base. Now, going back the other way, highlight those special effects. You can see Dr. White works out. But anyways, when you go this way, A minus, does it accept a proton, hydrogen, or donate it? Goes from A minus to HA. It's accepted a proton. Therefore, A minus is a base, and it's on the right. It's the conjugate base of HA, A minus. Now, let's look at HB plus. When it goes to its conjugate, B, this way, follow the blue line, does going from HB plus to B, is HP plus donating a proton or accepting a proton? Follow the H. Does it have one or does it give it up? And time's up, it gave it up. So that means HB plus proton donor is an acid. And because it's on the right side, it's the conjugate acid. All right, let's look at this. 4 points. Identify the acid-base conjugate acid. Test, if I were to put that, I'd print out the whole conjugate. Dr. White's being lazy. Conjugate acid and conjugate base in that reaction. So how do you do that? Will you identify the conjugates? What are molecules that differ by only 1 proton? Let's look at HCl. It's got a chlorine. Which one of these has a chlorine? That. So that must be its conjugate. If we look at ammonia, NH3, which compound on the right has the nitrogen? This one. So they're conjugates. Notice they only differ by H plus. For students, just count the hydrogens. One has 3, one has 4. And those are the conjugates. Now, by definition, everything on the left are either acids or bases. Everything on the right are conjugates. So immediately I can put conjugate. Now, if we look at W going to Y, HCl, does it donate a proton, lose it, or gain one? Count the hydrogens, 1 to 0. Oh, it lost one. It donated one. That means W is an acid. If we look at X, NH3, when it goes to its conjugate, NH4 plus, does it gain, accept a proton, a base, or donate a proton, an acid? Count the hydrogens, goes from 3 to 4. It accepted a proton. What's a proton acceptor? A base. Next, let's look at Y. When it goes back to its conjugate W, going this way, when Cl minus goes to HCl, does it accept a proton or donate a proton? Count the hydrogens. Went from 0, hold on, 0, I like that, to 1. It accepted a proton. And what is a proton acceptor? A base. And Y is called the conjugate base of this reaction. And finally, we have ZNH4 plus, the ammonium cation. And it goes from NH4 plus to its conjugate X, NH3. Has it donated a proton, acid, or accepted a proton, base? Count the hydrogens. Went from 4 to 3. I like how quickly I did that. 4 to 3. And it donated a proton. Lost one. What's a proton donor? An acid. And Z is the conjugate acid. And you should know how to do this. Oh, let's try another one of these. Hold on, let me do something. I'm in a habit of doing something and make students think that's the only way they are, and it's not. All right, now I'm going to have you try identify, like I did with a line, which are the conjugates. W, what is its conjugate on the right? X, what is its conjugate on the left, on the right? And you try that first, then I'll do it. Excuse me. Remember, conjugates differ by only one proton, H plus, but they differ by only a hydrogen. All right, my turn. Let's look at KOH, potassium hydroxide. It's got an oxygen. Well, both of these have oxygen, so let's skip that for a second. Let's look at S, H2SO4. This has a sulfur. This is the only thing that has a sulfur. So they have to be conjugates. And with that, that tells me this KOH, its conjugate is water. Now, by definition, on the right, those are the conjugates. So I'm going to write that in. Now, I'm going to let you try and figure out, is W an acid or a base? Is KOH an acid or a base? And is H2SO4 an acid or a base? If one's one, then the other is the other thing. And your turn. My turn. If we look at W, KOH, and it goes to its conjugate water, Z, does it gain a proton or lose one? Count hydrogens. Goes from 1 to 2. It's accepted, gained it, and that is a base. Now, if we look at X, H2SO4, it goes to Y. It had 2 hydrogens. Now it only has 1. Does it gain or lose a proton? Think a hydrogen. And the answer is it loses or donates a proton. What's a proton donor? An acid. Now, I'm going to let you figure out Y and Z. Is Y an acid or base? Is Z an acid or base? And when you're done, let me relaunch the poll. Let me know when you're done. Again, we're trying to find, is Y the conjugate acid and is or base, or is Z the conjugate acid or base? And if we look at this, now it's my turn. Y goes to X. Y has 1 hydrogen, X has 2. Has it accepted or donated a hydrogen proton? And the answer is it accepted it. And a proton acceptor is a base, and because it's on the right side, it's the conjugate base. And let's look at water going to KOH as conjugate. Water has 2 hydrogens. Potassium hydroxide, KOH, has 1. Has it accepted or donated? Goes from 2 to 1. Hopefully all said donate, give up. What's a proton donor? An acid. And that's how you do it. Yeah, if I look at the clock, oh no, I went a little over before our break. Let's take a 5-minute break. And I'll see you in 5. I can get up and stretch. I'm back. Ooh, sorry about the delay in getting back. All right, I'll go an extra minute or two. Won't cheat you out of your time. Now, you have the acid-base conjugate pair, and you should know how to identify them. And here's again, a conjugate base of an acid, a species that remains when an acid loses a proton, and a conjugate base acid of a base is a species formed when a base accepts a proton. And we did that. Now, next couple of slides, click. Will this be on a test? No, but you should know about this. Now, when it comes to acids and bases, not all acids and bases are created equally. We have what's known as a strong acid, and that means in the acid-base equilibrium, about almost 100% shifts or goes to this way. In other words, a strong acid says, I've got a proton and you're going to take it whether you like it or not. And some examples are sulfuric acid is a very strong acid, and hydrochloric acid are a strong acid. Now, let me remind you one of the great, in my mind, wonders of life, exciting wonders in our stomachs. Mine's down here. Hopefully yours is down below your body too, unless you're from outer space. But anyways, in our stomachs, we have cells, I guess, that make hydrochloric acid. It's amazing. It boggles my mind. See, my mind's getting boggled. Anyways, it makes hydrochloric acid that helps break down your food. I'll talk a little about that later in the semester. So strong acids say I have a proton and I'm going to give it to you. Now, there are weak acids in which the same equilibrium, the acid, when it reacts with a base, most of it stays here, doesn't react, only about 5%. Again, switches off, but this is something important for your life, the rest of your life you can use, and we call that a weak acid. An example of that is acetic acid, which is found in vinegar. If acetic acid was a strong acid, if you take any vinegar and something like salad dressing, you'd be in the hospital. But luckily it's not. It's a weak acid. By the way, do anybody know of anybody who does shots of vinegar? Yeah. But anyways, that's a weak acid. Now, same thing, you can have strong bases. And those are bases, usually hydroxides of the alkali metal and alkaline earth metals. That's group 1A and group 2A. And these are bases that say, give me your proton, whether you like it or not. And examples of that, again, switches off on strong and weak, are sodium hydroxide, NaOH, and KOH, potassium hydroxide. They're strong bases. Now, a weak base is one that says, could you give me a proton? I'm a proton acceptor. All right, you don't want to do that. That's okay. And example of that is sodium bicarbonate. And sodium bicarbonate, as you found out from the airbag lab, is in baking powder and baking soda. Again, switches off. Ooh, how did that get there? All right, hang in there. That's better. I had too many windows open. I couldn't do something I wanted to do. And there we go. All right. You should be aware of the association of water. Click the switch is sort of on, but it's important, not only for my class, but other classes. Water can react with itself. And when it does, one molecule is an acid, the other a base, and you have a proton transfer to form the hydronium ion and the hydroxide ion. Now, if you notice, the arrows aren't the same. That's because only very little amount goes to form the hydronium and hydroxide. But this little amount plays a tremendous role in our daily life. And this is called the association of water. Now, because I don't really teach it in this class, when you have equilibrium, there's a constant involved, a number showing how far one way or the other the reaction goes. And for water, it's called the ionization constant. K is constant, W water. Actually, it's named after me, KW. I wish. But anyways, this you should know. Oops. I even have it on the slide at the bottom. Hint, know this. The ionization constant is the hydronium ion concentration. And when you have these brackets around a molecule's formula, that means concentration, moles per 1,000 milliliters. This I won't, but the hydronium ion concentration times the hydroxide ion concentration equals, and that should be 0.0, 1.0 times 10 to the minus 14. It's a small number, but it's still significant. Now, KW, not named after me, but I wish it was, shucks. But anyways, this was created long before I was born. KW is affected by temperature. I am. Anyways, that number, and this is for room temperature, 25 degrees C. Let's look how we can use that. By points. If the hydroxide concentration, remember brackets in a chemical formula, closed bracket, like I have, the square means concentration. The hydroxide concentration is 1.0 times 10 to the minus third. Then what is the hydronium ion H3O plus concentration? Well, what are we being asked to find? What are we given? And as soon as you see concentration of OH minus and H3 plus, one of the things you should think of And hold on while I open it up. Important information, test number 4. We have the ionization of a constant of water is hydronium ion concentration. Oh, I made a mistake here. It should be 1.0 times the hydroxide is 1.0 times 10 to the minus 14. That you don't have to memorize. In the past, students would have to in my class. So we also know this. So what are we trying to solve for? The hydronium ion concentration. Well, we have this equation, and we're also given the hydroxide ion concentration equal 1.0 times 10 to the minus 14. Well, if I'm trying to solve for the hydronium ion concentration, I want it alone on one side. And how do you get rid of hydroxide? Remember, anything divided by itself equals the number 1, gets canceled out. Well, if I want to get rid of the hydroxide, because I'm trying to solve for the H3O plus concentration, I'll divide by that. However, whatever you do to one side, you have to do to the other. And I just did. OH minus concentration divided by OH minus number 1 cancels out. So I'm left with the hydronium ion concentration equals this. And now I know what the hydroxide ion concentration is from the problem. So I'll put that in. Now, since I grew up with a slide rule, I know how to do this calculation in my head, but you can do it in your slide rule in your calculator. And the number is this. And that's how you do it. And again, the key is knowing what are you being asked to find, what are you given, and also from important information, test number 4, KW, not named after me, but I wish it was. Every time I see it, I say, oh, I'm that great. They named something after me. I wish. But equals the hydronium ion concentration times the hydroxide, 1.0 times 10 to the minus 14. Remember, important information, test number 4, you'll be given that. Good news, you don't have to memorize it. Oh, this was fun. Let's try another one. All right, this is one of those I'm going to have you have some of the fun too. First thing I'm going to ask you, what are you being asked to find and what are you given? Your turn. Isn't it nice I share? Don't answer that. All I'm asking you to find is what are you given? What are you being asked to find? By the way, if you haven't figured it out by now, I've been secretly brainwashing you how to solve problems. Identify what you're trying to find and what are you given. Well, we're trying to find the hydronium ion concentration. We're given the hydroxide ion, OH minus concentration. And as soon as you see these two, you should remember, and let's go to important information, test number 4, hydronium ion concentration times hydroxide equal 1.0 times 10 to the minus 14. And therefore, I'm going to write that down right here. I know this. And therefore, I'm going to start with that. And I did. Now I'm going to give you a chance to figure out how to solve, not putting in the numbers yet, how to solve for H3O plus, meaning getting that alone on one side. All right, my turn. How do we get this alone on one side? We get rid of the hydroxide OH minus. Anything divided by self is the number 1. So I'm going to divide by OH minus, and that will cancel it out. But whatever I do to one side, I have to do to the other. And I did. So I'll rewrite this, H3O plus equals 1.0 times 10 to the minus 14th divided by the hydronium ion concentration, OH minus. I'll rewrite the top, this number. Well, we were given that, so I'm going to write that in. And if you put this in your calculator, remember Dr. White can do this in my head, it's 1.0 times 10 to the minus 3. And that's how you do it. All right, let's continue on. Now, it turns out knowing the hydroxide and the hydronium ion concentration is very important. And I'll be subtle again. Don't you love when Dr. White's subtle? You don't have to answer that. And let's talk about acidic, basic, and neutral solutions. What is an acidic solution? You should know this. An acidic solution is where the hydronium ion concentration, H3O plus, is higher, and we'll use the term, I'll show you symbolically, that arrow, V going that way, means in math greater than the hydroxide ion concentration. So if you have an aqueous solution, a solution which the hydronium H3O plus concentration, the amount is greater than the hydroxide, we call that acidic. The fluids in your stomach are acidic because the hydronium ion concentration is greater than the hydroxide. Now, a basic solution is just the opposite. The hydroxide ion concentration is greater than the hydronium ion concentration. And we call this a basic solution. Sometimes it's also called an alkaline solution, like in your alkaline batteries. And that, you know, the hydroxide concentration is greater than the hydronium concentration. Finally, there's one other term you should know, and that's a neutral solution. And a neutral solution has the hydronium ion concentration the same as the hydroxide ion concentration. Again, neutral solution, the hydronium ion concentration is the same as the hydroxide concentration. So let's look at this again. Acidic solution, hydronium ion concentration greater than hydroxide concentration. Basic solution, just the opposite. Hydroxide greater than hydronium ion concentration, H3O plus. And finally, neutral solution, hydronium ion concentration equals hydroxide. And you should know this. Hint, hold on. Ooh, a double hint. So we look at this, and if we went back to the problem we just did, let's look at one of these, like this one. Here, the hydroxide is 1.0 times 10 to the minus 11. The hydronium is 1.0 times 10 to the minus 3. Is that acidic or basic or neutral? Wow, that's hard to know. And it is. So what do? Well, it turned out chemists saw that. That's pretty hard. Is 10 to the 11th greater or smaller than 10 to the minus 3? So you got to know that, whether it's acidic, basic, or neutral. And that's hard. So guess what? Someone, one of these days, I got to find out who did. Honestly, I don't know. I apologize, but I don't know. Someone came up with what's called the pH constant. And of all the things that I'm going to teach you this semester, for your personal life, for your professional life, this is probably the most important concept I can teach you. And the pH constant, and I'll never ask you to define what pH is a scale. And it's called the pH scale. And it's a scale of small numbers that are used to specify the molar hydronium ion concentration. And this is important in aqueous solutions, but it's that important. And by definition, pH equals minus the log of the hydronium ion concentration. Now, logarithm is what power to the power of 10 would give you that number in the bracket. And this one is -1 times that number. Now, it's time for a special gift from Dr. White. Shh, don't tell anybody I'm being nice. Shh, be quiet. Remember, mum's the word. And that special gift, when hydronium ion is 1.0 times 10 to the minus x, the pH is x. If it's not 1.0, then I'd have to teach you, and students have problems grasping this, how to use logarithm function on your calculator. And my gift to you is, guess what? You don't have to use it, because on my test, I'll always give you the hydronium ion concentration starting with 1.0, and it'll always be times 10 to the minus x. And if that's the case, the pH is x. Now, pH goes from 0 to 14. The lower the pH, and I'm going to show you something nice in a second, the more acidic a solution is. The higher the pH, the more basic it is. Now, I won't ask you this, but this is a logarithmic scale, and pH 5 and pH 6, and we say, oh, that differs by one number. No, in logarithms, it's a power of 10 difference each number. And the pH is a power of 10 difference in acidity or basicity. Huh, I thought I had it here. Hold on. Well, I guess I don't. So I better get to my this is one I'm going to ask you to memorize because this is so important. This is something you can use the rest of your life. Here I have the pH scale. And it goes from 0 to 14. In the middle is 7. Below 7, that's an acidic solution. At 7, you have a neutral solution. Above 7, you have a basic solution. pH is never more than 14, never less than 0. Many years ago, I was manager in this one research group. I had about 14, 15 PhDs and master's degree chemists reporting to me doing research. I was at this company then called CHEMI, now it's AkzoNobel, and I was in charge of nitrogen derivative research for all North America for that company. And a chemist came in and gave me a report. And before we issue reports, section heads have to proof it. And actually, there's a form you sign off on. And you make sure there are no mistakes in there. And I looked at it, and he measured some pHs. And he had pHs of 18, 19, and 20. And I called him back into my office, had him sit down. I said, close the doors. When I closed the door, I had 2 doors because I had 2 labs. I could walk into either lab from my office. When I said that, that's not a good thing. And I asked him point blank, and I was really mad. And I've learned as a manager, you never scream because that doesn't help. But I was really mad. And I asked him politely, do you like working here? He said, yeah. And I gave him his report, and I said, if you ever give me a report again where the pH is below 0 or above 14, you won't be working here the next day. And he got the message real quick. And I said, go back and redo this. There are meters that you can use to measure pH, and he didn't calibrate it correctly. And I knew that. And he got the message real clear. Don't hand me that kind of garbage. An undergrad chem major would know better, not a PhD, a master's. He was a master's degree chemist. Oh, was I mad? But I didn't yell at him. I just politely said, do you want to be working here tomorrow? He got the message. All right, let's look at something fun. And as one of your colleagues said, the pH of soil you can measure. A common one I used to have until I tore it out, above ground swimming pool. The pH of the water you should measure. Now, if you look on the screen, they have the pH of different things. And if you look at HCl, hydrochloric acid, that's in your stomach. Pure acid hydrochloric is pH 0. Your stomach is acidic because there's an acid present, hydrochloric acid. In lemons and limes, more in lemons, there's citric acid. That has a pH of 2. Vinegar has a pH 3. Now, pure water has a pH 7.0. You are not going to get pure water out of the tap in your house. I don't know what the pH I have measured a long time of Chicago water, but one problem I had to solve was that a plant for a company I worked at, that was when I was a senior manager, research development manager at Borden Chemical, now Hexion. And part of my job was when there was a problem, one of the plants that nobody could solve, the research director would call me up and say, go solve it. And I would. And the way I solved the problem was it dealt with pH of a product. And the first thing I did when I got down there was, and this was in Cleveland, the plant was, I said, oh, you use water to make this product? What's the pH of your water? And it was summer and the pH was 8. Oh, the water was awful. But we had to take that into account and they didn't. Now, if you look at ammonia, which is a base, the pH is above 7, and that's why ammonia is a base. Well, not why it's a base, but it shows you it's base. And drain cleaner, there are different types of drain cleaner. The best one is made with sodium and potassium hydroxide. There's also acidic drain cleaner, which they don't show on here. And here's another one. And at 7, you're neutral. Below 7, like you see stomach acid, HCl. Tomatoes are acidic because they contain citric acid. Now, if you notice right here, there's something called acid rain. I should talk about that now briefly. If you look on there, the Wikipedia has a nice write-up of acid rain. And what is acid rain? That's rain, which is water, when the pH is lower than 7, way lower, like 4 or 5, or sometimes many years ago, below that. And where did this come from? The pollution from coal burning power plants in the Midwest and East. That would put into the air sulfur dioxide or sulfur nitrogen dioxide. And in water, in the clouds, that would react to make sulfuric and nitric acid, which would come down in the rain. And when you have a pH that low, that's acidic water, acidic rain, it would kill vegetation it goes on, like in forests. If it goes into rivers and lakes, it kills the fish in there and any other aquatic life. It damaged a lot of things, including farmers' fields. And finally, I'm trying to think, it was about the 1980s, the EPA, the government then, federal government, enacted laws, pollution laws, to cut down those emissions from the power plants, and that cut down the acid rain. All right, let's go back. You should know pH. If it's at 7, it's neutral. If it's above 7, it's called a basic solution. If it's below 7, it's acidic. All right, 6 points. If a solution has the hydronium ion concentration H3O plus equal 1.0 times 10 to the minus 4th, what is the pH of the solution, and is it acidic, basic, or neutral? So what are we being asked to find? pH. What are we given? The hydronium ion concentration. And if you look at important information, test number 4, you'll see pH equal minus the log of the hydronium ion concentration. And Dr. White's being real nice. Remember, if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. So let's go back and look at our problem. We know pH equals minus the log of the hydronium ion concentration. In our case, that's 1.0 times 10 to the minus 4. When you have one hydronium ion concentration, 1.0 times 10 to the minus x, the pH is x, so therefore the pH is 4. Everybody with me on that? That's my special gift to you. This way you don't have to use your calculator to figure that out. And there's a minus sign here. All right. Now, is that acidic, basic, or neutral? You need to know. This, I'm not giving it to you. This is one of those things I'm asking you to memorize. And if you notice, the pH is less than 7. And because of that, it's acidic. So the answer here is this is acidic. Let's do another one. And let's do this stepwise. You know what I'm going to do. Oh, I wonder why that. Hold on. I had a question mark that moved on me. It happens once in a while. Never know why. All right. Why don't you figure out what are you given? What are you being asked to find? Your turn. And the rest of your life, whenever you encounter a word problem, you know the first thing you're going to do is figure out what are you being asked to find and what are you given. That's going to help you. I actually had years ago a Chem 11, 1211 students who I was teaching the same thing, said, I wish I had you before I had math, because now I could not do word problems finally. All right, what are we being asked to find? pH, and also is it acidic, basic, or neutral? What are we given? The hydronium ion concentration equals 1.0 times 10 to the minus 11. And you know from important information, pH equals log, that's a G, of the hydronium ion concentration. And if you look at important information, test number 4, you see if the hydronium ion concentration is 1.0 times 10 to the minus X, then the pH is X. So I'm going to let you try and solve this. Your turn. Then I'll do it. By the way, the teaching term of what I've been doing when I give you time to do stepwise is called fading prompts. And also I give you a lot of practice. Oh, I'm giving away all my secrets today. All right, I think, well, let me rerun the poll just to be sure. Everybody done? And the answer is yes. Now, I'm going to go a little over 5-10 minutes later than I normally do because I want to cover one more thing. And it's for your benefit, not mine, because hey, I'd rather be watching TV now. Not really. But let's do this one first. pH minus the log of the hydronium ion concentration. In this case, it's this number, 1.0 times 10 to the minus 11. When the hydronium ion concentration is 1.0 times 10 to the minus X, the pH is X. What is X? 11. Now, is it acidic, basic, or neutral? You need to know. This chart. When the pH is at 7, it's neutral. When it's above 7, it's basic. When it's below 7, it's acidic. And now you got to do some high level thinking. Well, is 7 below or above? Is 11 and below or above 7? And time's up, they all picked above, and therefore this is a basic solution. Yeah, I see someone with a question. I better look at it. Oh, the answer actually beat me to it. All right, let's do one more. And after this, then we'll call it a day, unless you're coming to my office hour tonight. Yep, 8 points. So let's look at this. 8 points. If the OH hydroxide concentration, OH minus concentration equal 1.0 times 10 to the minus 4th, what is the pH of the solution? And is it acidic, basic, or neutral? So what are we trying to find? pH. What are we given? OH minus hydroxide ion concentration equals this number. And you know from important information, test number 4, pH is minus the log of the hydronium ion concentration. Uh-oh, we don't have this number. What do we do? Oh no, what do I do? Well, you also look at important information, test number 4, and you remember the hydronium ion concentration times the hydroxide equals 1.0 times 10 to the minus 14. And that means you need 2 steps. And step 1, I didn't even put this in the important information, so you'll have to remember this. I'll figure out, I'll solve for hydronium ion concentration. So how do I do that? Well, I know hydronium ion concentration times hydroxide ion concentration, which I have, equals 1.0 times 10 to the minus 14. Look familiar? We just practiced this. And if I'm solving for hydronium ion concentration, I want it alone. Want it to look nice. Hold on. On one side. So how do I get rid of the hydroxide? Anything divided by itself equals the number 1. See, it says it on the screen. It cancels out. But whatever I do to one side, I have to do to the other. This cancels out. I know the hydronium right there, so I can put that number in. That's 1.0 times 10 to the minus 4. And you can pick up your calculator. Dr. White knows how to do this in his head. And the hydronium ion concentration is 1.0 times 10 to the minus 10. Am I done? No, I need to find pH. And now I'll do step 2. Determine pH. Oops. And remember, pH equals minus the log of the hydronium ion concentration. We just calculated that right here. So I'll put that in. And remember my special gift. Shh, don't tell anybody, I'm being nice. Shh. But when the hydronium ion concentration, H3O plus, is 1.0 times 10 to the minus x, the logarithm is x. In this case, x minus x is minus 10, x is 10, the pH is 10. Now, you also have to answer, is that acidic, basic, or neutral? And you need to learn this chart. And pH goes from 0 to, that's an ugly looking 7. Hold on, let me repeat that. That's better. When pH is 7, that's a neutral pH solution. When it's above 7, it's basic. When it's below 7, it's acidic. And if you notice, 10, I hope you all figure, is above 7. Therefore, this is a basic solution. And let's go back and review this, and then I'm going to let you go. Thank you for staying a little late today. What are we being asked to find? pH. But we're given the hydroxide ion concentration. To calculate pH, you need the hydronium. Therefore, we need 2 steps. In step 1, we determine the hydronium ion concentration using Kw, the water ionization constant, named after me. No, not really, I wish. But every time I see it, I feel good. And that's this equation. You solve for hydronium, getting it alone on one side, and you calculate that number. Now we do step 2. We have the hydronium ion concentration, pH equal minus the log of the hydronium ion concentration. We calculated it there, so we put that number in. And when the minus the log is 1.0 times 10 to the minus x, the pH is x. In this case, minus x is minus 10. The pH is 10. Is it acidic, basic, or neutral? You need to know that 7 pH is neutral, below 7 is acidic, above 7 is basic. In this case, 10 is above 7, it's basic. And with that, we're just about on track. Remember, tomorrow morning, I will send out the password for test number 3. Well, I gotta get that finger fixed. And about 8 a.m. or maybe even a little earlier, you'll have until Friday, 4 p.m. to upload your test number 3 answers as a single PDF file. Make sure you check it before you do, and you've got all your answers in that PDF file. And by Sunday afternoon sometime, because I also have a big test in my other class I have to grade, they're due at 4 p.m. Friday also. This weekend, I'm going to be grading, lots of grading. But I will send out the email saying your score is in Blackboard. And also by that time, I'll send out an individual email with each point you got for each answer on that test. Also, sometime tomorrow, I'll be posting the information about test number 4, which I have to finish the material by Tuesday. Don't forget, hand-in labs. They're easy points. I'm going to talk more about people who haven't handed in labs, and a special nice thing I'm going to do for everybody who haven't tomorrow. And with that, unless you're going to stop by my office hour tonight, and even if you are, I'm still going to say, gang gesund, goodbye. Stole that from Granny to Beverly Hillbillies. Bye.